Everyone, in this video I am going to explain the logical instructions, different logical instructions available in 8085 microprocessor. Okay, so let's start. So in 8085 microprocessor, the logical instruction available are basically for ending, logically ORing, and logically XORing. Okay, so this group of instruction, logical instruction, performs logical operations on data that is there in the register, or it may be there in the memory, or it may be in immediate after the instruction, that is immediate data, as well as there are few instructions which will do some logical operation on the conditional flags. Okay, just like addition or subtraction instruction, these logical instructions are also basically, for each instruction basically there are three categories. One, as like in addition is done with the data stored into the register, any one of the register. Addition instructions are there in there to add the content of the any memory location whose address is of course in the HL register pair. And also addition instructions are there for adding immediate data. Similarly, and logical instructions are also for logically sending, XORing, and ORing with the data stored into the register or stored into the memory location whose address is in HL register pair, and immediate data. Along with, there are few logical instructions for data on the conditional flags. So instructions available only for ending, ORing, XORing, also complementing. But there is a special instruction under this group which is rotating, or also called shifting, as well as there is one more instructions, one set of instructions which is for comparing two binary or hexadecimal data. Okay, now in this, under this instruction also this flag, since it is a logical operations, all the flags will be affected, and as like addition or subtraction instruction, here also to perform any logical operation at least two data is required. There are few exceptional cases, I will mention that, and where there is two data are required. Say for example ending, to do the ending you need to have at least two data, and out of the two data or operand, one of the operand must be there into the accumulator already, as it was the case for addition or subtraction instruction as well. So one of the data here also must be there in placed into the accumulator, and another data, the second data, can be in the memory or register or immediate after the instruction. Okay, and the result always again something like addition or subtraction instruction, results are also placed into the accumulator. Actually results is replaced into the accumulator because before instruction accumulator holds one of the operand, after instruction, after execution of the instruction, accumulator hold the results. Okay, so let's start with the instruction for basic logic function. Here the basic logic function includes ending, ORing, and XORing. Okay, these three only. There is no instruction for ending, there is no instruction for ORing, there is no instruction for XORing. Okay, so there are instructions for end, OR, and XOR. These three basic operations, logic operations. Okay, to start with the instruction for ending. So instruction for ending is for doing the ending operation with the data placed into any one of the register along with the content of the accumulator. The instruction is ANAR. So ANAR means logically ended the content of the register R. Okay, so this is the symbol for logical AND. Okay, so the content of the register R, specified register R, this R can be again the same as that was in the previous cases. This R can be A, accumulator A, or register B, C, D, or E, or H, or L. So the content of that specified register R are logically ANDed with content of the accumulator, and result is placed into the accumulator. So as like ADAR, SABAR, ADDR, SUBR, something like that, ANAR is also 1-byte instruction. And here, since it is 1-byte instruction, and as well as the data is stored into the specified register, so therefore the machine cycle is 1, and in that machine cycle, number of the state, that is the number of clock periods required, is 4. And since the source of the data is, remember here you are pointing only the data which the second data, because microprocessor already understood that one of the data is already there into the accumulator. So before doing these operations, you have to place one of your operand into the accumulator, and it is actually looking for the second data only. In this instruction, it is looking for the second data only, and the second data is there in the register R. Directly that R is, the specified register is given along with the instruction, so therefore it is register addressing mode instruction. And in this instruction, all the flags will be affected. Particularly, carry flag will be cleared and auxiliary carry flag will be set. This is an exceptional case. So in this instruction, carry flag will be cleared and auxiliary carry flag will be set. Set means set to 1. Okay. So in the instruction format, since it is 1-byte instruction, the format is 1010 0SSS. This SSS again for the source register A, B, C, D, E, H, L, and follow the same truth table that I mentioned in my previous video. Okay. So accordingly, there are 7 different instructions. Okay, 7 different instructions. So those instructions are ANA A, ANA B, ANA C, ANA D, ANA E, ANA H, ANA L. Okay. So ANA A means a content of accumulator is ANDed with accumulator, and result is into the accumulator. Okay. So for A, it is 111. So therefore 1010, which is A, and 0111, which is 7. So opcode is A7. So it will be something like, for example, I am just showing with an example. Suppose A, okay, I'll show these examples in the second instruction. Say A and A B. Okay, for the A and A B I am showing. Say for A and A B I am showing. For that A is suppose holding. A suppose holding. Say just example 56 hex. So 56 hex means it is your 0 1 0 1 for 5, and for 6 0 1 1 0. Okay, and suppose register R is for suppose B, my B, and B suppose hold say 78, for example 78 hex. 78 hex is 0 1 1 1. So 0 1 1 is for 7, and so 1 0 0 0 is for 8. Then after the execution of A and R, the result will be goes to accumulator. So after A and A B, the result will go to the accumulator. So what will be the result? It will be, let us see, so it is bit by bit ending. So 0, first is 0 ended with 0 is 0, then 1 ended with 1 is 1, 1 ended with 0 is 0, 1 ended with 1 is 1, 1 ended with 0 is 0, then 1 with 0 0, 1 with 0 0, 0 0 0. So therefore the result is here this is your 5 and 0, so 50. Result is here 50 hex. Result is here 50 hex. So this is just an example. Okay. That way it does. Okay. So these are the different instructions. Next, as like add m, similarly a and am. So m again, as I have mentioned in my previous videos, that m is nothing but the memory location whose address is currently stored into the HL register pair. Okay, so it is m and it is indicating the memory location, but whose address is in HL register pair, so therefore it is register indirect. So logically ended the register indirectly. So the meaning of this is the content of the memory location whose address is in HL register pair or currently stored in the HL register pair are logically ended with the accumulator, and a result is placed into the accumulator. So this is also 1 byte instruction, but in this case, since the data is actually there in the memory location whose address is in HL register pair, so machine cycle is 2. And in the first machine cycle it requires 40 states, that is 4 clock periods, and in the second machine cycle it is 3. Okay, that are total of 70 states. And addressing mode, it is a register indirect. Here also flag, all the flags will be affected. Particularly carry flag is cleared, that is 0, and auxiliary carry flag is set, that is set to 1. And in this case, since it is only one instruction format which is only 1 byte, that is opcode, and the instruction format is 10100110, which is A6 hex. This is A6 hex. Sorry. Similarly, there is the third instruction for ANDing, which is ANI data. So this data is again the 8-bit data immediately given after the instruction. So that is why it is immediate addressing mode instruction. So the meaning is logically ended immediately. So this is a 2-byte data, that is for opcode ANI. I mean opcode is for ANI, and another is a byte is for the 8-bit data. Second byte is for 8-bit data. So byte 2 is actually your data. So the content of the byte 2 of the instruction are logically ended with the content of the accumulator, and a result is placed into the accumulator. Okay, and it is 2 byte, as I mentioned, machine cycle of course 2, and this state for the first it is 4 and the second it is 3. So there are total of 70 states. And addressing mode, immediate addressing modes, here also the flag all, and particularly carry flag is cleared and auxiliary carry flag is set to 1. And instruction format, there are 2 byte, since it is 2 byte instruction, so in the instruction format there are 2 bytes. First byte is of course opcode, and second byte is the 8-bit data. So opcode here is 11100110, which means E6 hex. Okay, so these are the 3 instructions: ANAR, ANAM, ANI data. These are the 3 instructions for logically ending or logically ended. Okay, as like ending, there are similarly 3 instructions for ORing: ORAR, ORAM, and ORI data. Okay, so again the same thing as like ANAR. Here is ORAR, logically ORed with the register. This is the symbol for logical OR, and this R is again the specified register, one out of the 7 different register, accumulator B, C, D, E, H, or L. So the content of this register, specified register R, are logically ORed with the content of the accumulator, and result is stored into the accumulator. As like ANAR, this is also 1 byte, machine cycle 1, T state 4, register addressing mode, flag all. But in this case, both the carry and auxiliary carry flags are set to 1. Like in ANDing operation, carry flag is cleared, but auxiliary carry flag is set. But in this ORing instruction, both the carry and auxiliary carry flags are cleared. And in the instruction format, the 1 byte, that is the opcode 10110 SSS, again SSS for the source register R. So there are 7 instructions: ORA R, ORA A, ORA B, ORA C, ORA D, ORA E, ORA H, and ORA L. Okay, so for example, ORA A is ORed with A, that is content of A is ORed with content of A, and result is stored into the A. So for A it is 111, therefore it is 1011, that is B, and 0111, that is 7. Okay, therefore the code is B7. Similarly for all this. Similar, like ANAM, there is ORA M also. So this M is again the memory location whose address is in HL register pair. So the content of the memory location whose address is in HL register pair are logically ORed with accumulator, and content of the accumulator and result is stored into the accumulator. So as like ORA A and M, here also the same thing: number of byte 1, machine cycle 2, T state 7, addressing mode, register indirect, flag affected all. Again, since it is OR instruction, both the carry and auxiliary carry flag set to 1, cleared to 0, both auxiliary carry and the carry flag are cleared to 0, and instruction format here is 1011 0110, which is B6 hex, the opcode. Similarly, ORI data, that is logically ORed the immediate data given after the instruction with the content of the accumulator. So which is the byte 2 of the instruction, the content of the byte 2 of the instruction are logically ORed with the content of accumulator, and result is placed into the accumulator. Okay, so byte number of byte 2, machine cycle 2, T state 7, addressing mode immediate, flag affected all, but both the carry and auxiliary carry flag get cleared. And in the instruction format, there are 2 byte. First byte is opcode. And the second byte is the 8-bit data. So opcode is here 1111 0110, which is F6. Okay, which is F6. Okay. Then similarly, there are 3 different instructions for XOR. Okay, so this is the symbol for XOR. So XOR R, XOR M, XOR I data. Okay, so XOR R means the content of the specified register R are logically XORed with the content of accumulator, and result is placed into the accumulator. So like ANAR, ORAR, it is also 1 byte instruction, machine cycle 1, T state 4, and addressing mode register addressing, flag affected all, and here also both carry and auxiliary carry flag is cleared. Instruction format, here it is 10101 SSS, again SSS for your source register A, B, C, D, E, H, or L. Okay, so different instructions are XOR A, XOR B, XOR C, XOR D, XOR E, XOR H, and XOR L. Okay, and say for XOR D, it is D, content of register D is XORed with content of accumulator, and result is stored into the accumulator. Okay, so for D it is 0 1 0, therefore 1010 1010, that is AA hex. Okay, so next is XOR M. Again, M is the memory location whose address is in HL register pair. So the content of the memory location whose address is in HL register pair are logically XORed with the content of the accumulator, and result is stored into the accumulator. So this is also 1 byte, machine cycle 2, T state 7, flag all, but carry and auxiliary carry flag both are cleared, and instruction format, it is 10101110, which is AE hex. Okay, like ANI data, ORI data, similarly XRI data also, which is the byte 2 of the instruction, which is 8-bit data. So the content of the byte 2 of the instructions are logically XORed with accumulator, and result is stored into the accumulator. This is 2-byte instruction, message equal to T state 7. Flag all, both the carry and auxiliary carry flags are set to cleared to 0, and in the instruction format it is 110110, which is EE hex. Okay, so these are the 3 different instructions for 3 different logical operation, basic fundamental logical operation: ending, ORing, XORing. ANA for ending, ANAR, ANAM, ANI data; for ORing, ORAR, ORAM, ORI data; and for XORing, XORAR, XORAM, XORI data. So total of 9 instructions. Now in the second category of logical operation, there are instructions for comparing. Okay, comparing instructions. So here the things to be understood is how we do comparing two data. Suppose there is an X and Y. These are the two data. Suppose X and Y are the two different data which are to be compared. Compared means whether both are equal, or X is greater than Y, or Y is greater than X. That is what is called comparing. Now how we do comparing generally? We do comparing first what operation we do for comparing two data logically. We do subtraction operation actually for comparing. What we do, we subtract one from the another. Say X, what we do is we subtract one from the another. Say X minus X minus Y. Now if it is equal to say 0, then what is the result? X is equal to Y. But if X minus Y is not equal to 0, so not equal to 0, okay, not equal to 0, so this is the not symbol, not equal to 0. So not equal to 0 means what? It can be either positive or negative. Suppose the result is positive. If the result is positive, then X is, this means X is greater than Y. Okay. Similarly, if the X minus Y is negative, then your X is less than Y. Right? This is how we do comparing in general. Now in Microprocessor 8085 also the same operation is being performed while comparing two data, that is the subtraction operation. Now remember, there is instruction available for subtraction as well, like SUBR, your SUBM, SUY data. There are 3 instructions without borrow. Similarly, there are 3 instructions with borrow for subtraction, is your SBBR, SBBM, SBI data. Those are 3 subtraction instruction for the subtraction instruction through borrow also. Okay, so there are total 6 subtraction instructions. But along with there are compare instruction, but in the compare instruction also the operation is performed is the subtraction. The thing is that while doing the comparing instruction we don't look for the result, but we need the decision on the result. But in subtraction instruction we need for the result. Say for example, if I would like to subtract 5 from the 7 minus 5, where I am looking for the result is 2. But if I am comparing 7 and 5, I will do the same operation 7 minus 5, but I am not interested in the result. Rather I am interested the condition of the results, whether the result is 0 or non-zero. If 0, it is equals. If not, then whether the result is positive. If positive, the first is greater than the second. If negative, first is less than the second. Okay. So that is the basic difference between subtraction instruction and comparing instruction. Similarity is there. Similarity is subtraction also do the subtraction instruction, and compare instruction also does the subtraction operation. But in difference is, in subtraction operation result is placed into the accumulator, but in compare instruction accumulator remain unchanged. Okay, accumulator remain unchanged. That means we don't the result is not subtraction result is not goes to the accumulator. Rather, depending on the result, conditional flags will be affected. Okay. So now if the subtraction results, the ones doing the subtraction, if the result is 0, then accordingly Z flag will set to 1. Z is 0 flag. If the result is 0, so Z flag is so here Z flag is set to 1 if the content of the list, if both the datas are equal, that is the result is 0, then Z flag is set to 1. If result is non-zero, if the result is non-zero, then what will happen? If result is non-zero, there can be either positive or negative. Okay, suppose the result is positive. Result is positive means x is greater than y. Okay, so while x is greater than y, during the subtraction there is no borrow. So that means, as I mentioned in the subtraction instructions, that for borrow also it indicates the carry flag. If result is positive, that means x is greater than y, so therefore no borrow, therefore carry flag is reset. Now if result is negative, then x is less than y. If x is less than y, then there affects the borrow, that means carry flag will set to 1. So after the execution of these instructions, we will look into the Z flag and the carry flag. If Z flag is set to 1, that means both the datas are equal. If the carry flag is set to 1, that means content of the accumulator is less than the content of the specified register, because to do any operation, as already I mentioned, any one of the operand must be into the accumulator. So always the first operation, as like in the subtraction instruction, always the data are subtracted from the accumulator. So here also for comparing instruction also, the subtraction is always from the accumulator. So accordingly there are 3 instructions: CMPR, CMPM, CPI data. So CMPR, which is compare specified register R. So what operation is performed? As I mentioned, it is subtraction. So the register specified register, content of the specified register R are subtracted from the content of the accumulator and accordingly status flags are set to set according to the results of the subtraction, but the result is discarded. That means the content of the accumulator remain unchanged. That means result does not go to the accumulator. Now if both the contents are equal, then Z flag is set to 1. If content of A is less than content of R, then carry flag is set to 1. So looking at the Z or carry flag, we can say whether A is equal to R, the content of A is equal to content of R, or content of A is greater than content of R, or content of A is less than content of R. Okay. So this is also 1 byte instruction, machine cycle 1 to state 4, addressing mode register addressing, flag all, but all the flags, since the operation is subtraction, all the flags will be affected, but we will look into the carry and Z flag. So since it is R, CMPR, R is all the register A, B, C, D, E, H, L. So instruction format, byte 1, it is 10111 SSS. So accordingly CMPA, CMPB, CMPC, D, E, H, L. Okay, and these are the different opcodes. Again, SSS is for the source register R, for accumulator it is 111, for B 000, for C 001, and so on and so forth. Similarly CMPM. The CMPM M is again the memory location whose address is in HL register pair. So it is comparing the data, comparing the data stored into the memory location whose address is in HL register pair along with the accumulator. So the operation is again perform subtraction. So the content of the memory location whose address is in HL register pair are subtracted from the content of the accumulator, and status flags are set according to the results, but the results are discarded, and the content of the accumulator remain unchanged. So this condition is same. Okay, here the number of byte 1, machine cycle 2, T state 7, addressing mode register indirect, and opcode is BE hex. Opcode is BE hex. Okay, to compare an immediate data, the instruction is CPI data. So this data is an 8-bit data, which is the byte 2 of the instruction. So here the content of the byte 2 of the instructions are subtracted from the content of the accumulator, and the status flags are set accordingly, and result is discarded, and content of accumulator remain unchanged, and the condition is same. So this is 2 byte instruction, machine cycle 2, T state 7, flag all, particularly Z and carry flag will be looked into, and the instruction format it is FE hex, the opcode. Okay, so these are the 3 instructions for comparing 2 datas. So try to understand the difference between subtraction and the compare instruction. Subtraction instruction similarities, subtraction instruction does the operation subtraction, compare instruction also does the operation subtraction, but in subtraction instruction we look into the result, so result is replaced into the accumulator, and in compare instruction we are not intending to towards the result, rather we are going for the decision whether greater or equal or less. So therefore in compare instruction the result is simply discarded, that means the content of the accumulator remain unchanged. Okay, so accordingly there are CMPR, CMPM and CPI data, these 3 comparing instruction. Next is the rotate instruction or shifting instruction. So this is very interesting instruction. This instruction is something like your shift register. Okay, as like in shift register in digital electronics, and that is either shifting right or shifting left. Here also instruction for shifting left as well as shifting right, number 1. Number 2 is which data will be shifting, right or left. It is always the content of the accumulator. So you cannot shift or shift left or right the data stored in any other register except accumulator, or you cannot shift the data directly stored into the memory. So if you would like to shift a data either left or right, it has to be into the accumulator, and it is understood to the microprocessor that data is in accumulator. So it is, all these rotating instructions are of implicit addressing mode. That means it implied the source as accumulator. That is second point. Third point is that how many bit is being shifted in one instruction. So once you execute one instruction, it will shift always one bit towards the left or right. Okay, it will always shift one bit only to the left or right. Next, fourth thing is, while shifting left or right, there are two types of instructions. One is without carry, that means it does not considering the carry flag. Another is with carry, that is throw carry, that means it will also incorporate the carry. Carry flag is, the content of the carry flag is also shift. Okay, so accordingly there are two instructions primarily, that is for shifting right, rotating right, and rotating left. And further, rotating left is without carry and with carry. Rotating left also without carry and with carry. So there are a total of 4 instructions. So number 1 is RLC, which is rotate left without carry. Okay, rotate left without carry. So this is the pictorial representation of the shifting. As I mentioned, the shifting operation is performed, or rotating instruction is performed on the content of the accumulator. So data has to be there into the accumulator. Say this, suppose this is your accumulator. Okay, this is your accumulator, 8-bit accumulator. The bit positions are A7, A6, A5, A4, A3, A2, A1, A0. Okay, A0 is your LSB, least significant bit, and A7 is your most significant bit. Now when you execute RLC instruction, rotate left without carry, then what will happen? The bit A0, suppose 1 is there, it will go to the A1. If 0 is there, 0 is go to the A1, like that. So A0 shift to A1, A1 goes to A2, A2 goes to A3, A3 goes to A3 goes to, oh sorry, here. Okay, so A0 goes to A1, A1 goes to A2, then your A3 goes to A4, A4 goes to A5, A5 goes to A6, A6 goes to A7. Now where does A7 will go out? A7 will go out to the carry flag. Along with this same A7 will go to your A0 also, because A0 was lying vacant now. Because A0 goes to A1, this position was vacant. So A7 goes to carry as well as A7 goes to accumulate A0. Okay, so that is a it is pictorially or logically it is denoted as AN plus 1 is coming from AN. That is, the content of AN is shifted to AN plus 1. Suppose it is N is 0, A0 goes to A0 plus 1 A1, A1 goes to A2, A2 goes to A3, A3 goes to A4, like that. And A7, the last MS bit, is goes to A0 as well as to the carry flag. Okay, so the content of the accumulator is shifted left by 1 bit. The 7th bit, A7, of the accumulator is shifted to the carry bit as well as to 0 bit A0 of the accumulator. Okay, so this is the number 1 byte instruction, machine cycle 1 tested for addressing mode. As I mentioned, it is implicit addressing mode, and flag affected only the carry, as although it is does not shift the carry flag, that is why it is RLC is rotate left without carry, but it includes the carry flag. So carry flag get affected, because there may be something else in the carry flag. Okay, so that will pushed out, and A7 will occupy the carry flag. Okay, and in the instruction format it is 0 0 0 0 0 1 1 1, that is 07 hex. Okay, that is rotate left without carry. Similarly, rotate right. So rotate right is, it will shift towards the right by 1 bit. Accumulator content is shift by 1 bit. That means A7 will go to A6, A6 will go to A5, A5 will go to A4, A4 will go to A3, A3 will go to A2, A2 will go to A1, A1 will go to A0. Now where A0 will go? A0 will go to the carry flag as well as to A7. Okay, A7. So AN comes from AN plus 1, and carry and A7 comes from A0. Okay, so this is also 1 byte machine cycle 1 T state 4 addressing mode, implicit addressing mode, and carry flag is affected. Instruction format, it is 0F opcode. 1 byte instruction, so therefore in your instruction format there is only 1 byte. Next is with carry, both left and right. So RAL is rotate left, throw carry. Okay, so what will happen in case of your RLC is rotate left, as like this rotation in your RAL, also the same operations. A0 will go to A1, A1 will go to A2, A2 will go to A3, A3 will go for A4, A4 will go to A5, A5 will A6, A6 will go to A7, A7 is goes to carry flag. In case of RLC, A7 also goes to A0, but here since it is throw carry, so A7 goes to carry flag, and whatever be the content of carry flag is pushed out and will go to the A0. That is the difference between RLC and RAL. RLC is without carry. A7 go, in case of RLC, A7 goes to carry flag as well as A7 goes to A0. But in RAL, A7 goes to carry flag and carry flag goes to A0. Okay, that is why logically this. So the content of the accumulator is shifted left by 1 bit through carry. The 7 bit of the accumulator is shifted to the carry bit, and carry bit is shifted to the 0 bit of the accumulator. So all the conditions are same. 1 byte machine cycle 1 T state 4, implicit addressing mode, flag carry, instruction format, it is 17 hex is the opcode. Okay, so just like RC rotate right without carry, there is instruction throw carry for the rotate right, that is RAR. Okay, so here also the rotating is like RRC. So it is A7 to A6, A6 to A5, A5 to A4, A4 to A3, A3 to A2, A2 to A1, A1 to A0. Now A0 will go to the carry and carry will go to A7. Okay, here also the same thing, opcode is 1F hex. Now these rotating instructions are useful first if you would like to shift the content of the accumulator, when you would like to shift the content of the accumulator, like for example converting binary to gray. Okay, so the binary number will be stored into the accumulator, then you shift it and say whatever be the data you need to convert to the gray code. Suppose you stored it into the register B or any of the register, then copy of the same data placed into the accumulator, then rotate it towards the right, then do the XORing after rotating the data along with the content of say B. If you store the data into the B, then it will give you the gray code, binary to gray code. Okay. Or this rotating instruction is also useful for multiplications. How? Because if you see the multiplication of any 8-bit data with say 0, or with 0 is same only, with 2, with 4, because 2 is 10, 4 is 100, 8 is 1000, then your 16 is 140, 0000, like that. If you would like to multiply any data with with 2, 4, 8, 16, like that, that is essentially a shifting if you look at the multiplications. Since in 8085 there is no such multiplication instruction, direct multiplication instruction, only addition and arithmetic instructions are available only for addition and subtraction. So multiplication you can do by successive addition, but if particularly the multiplication is by, any data multiplied with say 2, 4, 8, 16, you can perform that multiplication using this rotating instruction. Okay. Next, number 4th category of the logical instruction is known as miscellaneous logical instruction. So in this miscellaneous logical instructions, there are particularly 3 instructions. Okay, one for the complementing the content of accumulator, another one is for complementing the carry flag, another one is for set the carry flag to 1. So first one is CMA. So this complementing or not, logically not complementing, this complementing instruction is available for only the accumulator, content of accumulator only. You cannot complement the content of B or C or D or E or H or L or the content of memory location directly. If you would like to complement the data, it has to be placed into the accumulator before. Okay, so once CMA instruction is there, microprocessor understood that the data is there in the accumulator and it needs to do the complementing of the content of accumulator. So complementing A bar, so content of accumulator is complemented, once complement. It is only once complement. If you would like to do the 2's complement, how will you do? First you do the 1's complement and then add 0, 1. So how will you add 0, 1? Simply you can execute INRA or ADI say 0, 1. Okay. So 1's complement the content of the accumulator is obtained and the result is placed into the accumulator. So here is number of byte 1, machine cycle 1 is step 4, and since it is only with the accumulator, it is implicit addressing mode. Accumulator is implied here, and opcode is 2F hex. Okay. Similarly, the CMC is for complementing the carry flag. Whatever be the content was there in the carry flags, it gets complemented. 0 goes to 1, 1 complemented to 0. Okay. So it is 1 byte, machine cycle 1 to step 4, addressing mode implicit. Flag is only the carry, and it is byte 1 opcode. Instruction format, it is only 1 byte, which is the opcode, and the opcode is your 33F hex. There is another instruction is STC. So STC is set the carry flag to 1. That means carry flag will be forcefully 1. Okay. Here also the same thing. Opcode is here it should be. Here it should be 0, 0, 1, 1. This should be 0. There is a mistake. This should be 0. So it is 37 hex. Okay, opcode is 37 hex. Now, what is the important or requirement of this instruction? Suppose in some operations, particularly while doing the rotating instruction, it is required. Sometimes we need to make, or we need to have carry flag forcefully 1 or carry flag forcefully 0. Okay, if we need to have carry flag forcefully 1, then what I will do, I will execute this STC instruction. It will make carry flag forcefully 1. Now, if I would like to have carry flag reset, that is 0, then there is no such instruction directly to make carry flag 0. So, what I will do, I will first make carry flag 1 by using STC, then using CMC I will make carry flag 0. So, to make carry flag 0, what I will do, first STC, then CMC. Okay. So, these are the all logical instruction, that's all. Okay. So, logical instructions are primarily for the basic logical operation. Basic logical operations are ANDing, ORing, XORing. There are three instructions for each of these three. For ANDing, ANAR, ANAM, ANI data. For ORing, ORAR, ORAM, ORI data. For XORing, XORAM, XORAR, XORAM, XORI data. Then comes your compare instruction. So, for comparing two data, there are CMPR, CMPM and CPI data. Then there are your rotating instruction. Rotating instruction is without carry, with carry, rotate left and rotate right. For rotate left without carry, RLC. For rotate right without carry, RRC. For rotate left with carry, RL, and for rotate right with carry, RAR. Then comes some miscellaneous logical instruction, under which there is complementing the accumulator CMA, complementing the carry flag CMC, and set the carry flag to 1 STC. That's all. Hope you understood. If you have any query, kindly contact me. Thank you.